So we're going to talk about angular momentum in this video. Your objective is that students will be able to recite the definition for and equations related to angular momentum and its conservation. So first let's review linear momentum, the momentum we talked about previously. When we talked about it, we were talking about linear momentum, and that was mass times velocity. So that's only for objects moving in a straight line, not things moving circularly or angularly, like we've been talking about lately. So we need to talk about angular momentum, not linear momentum anymore. So angular momentum is a little bit different in that it's defined as the moment of inertia times the angular speed, as long as it's a symmetrical object rotating around a fixed axis through the center of mass. So think of moment of inertia as kind of like rotational mass and angular speed as velocity. So you still end up having something like mass times something like velocity. And the equation is L equals I omega. Omega is that curvy W. I stands for the moment of inertia measured in kilogram meter squared, as it was before. The curvy Greek letter omega is this thing right here. I'll get the laser pointer. There we go. This guy right here. It's Greek letter lowercase omega, stands for angular speed. And capital L is the angular momentum measured in kilogram meters squared per second. I don't know why angular momentum is labeled L. Moving on. Angular momentum is related to torque, like anything is rotationally. So we can write the equation for angular momentum in terms of torque. So the net torque equals, net torque, sigma tau, equals the change in angular momentum divided by the change in time. Or if you're a wordy person. There we go. Net torque is the change in angular momentum over the change in time. So the more net torque there is, the more change in momentum there will be, angularly. This leads to the law of conservation of angular momentum. Previously, when we talked about linear momentum, we talked about the conservation of momentum. And the same kind of applies here, but it's a little bit different since it's moving circularly. When using that net torque is equal to a change of momentum equation, if the net torque is zero, like if you have multiple forces acting on it to make the net torque zero, then the change in angular momentum has to be zero mathematically. So this means that when there's no overall torque acting on an object, the angular momentum will not change. It has to stay the same. This is called the conservation of angular momentum. It'll stay the same. In other words, the product of moment of inertia and angular speed must always equal some constant. So if we have the moment of inertia times the angular speed, omega, that has to equal a constant. And there's kind of a consequence from this. This means that if one of these two things changes, if the moment of inertia or the angular speed changes, the other has to change in the opposite way to keep that constant the same. In other words, if something's speed increases, then its moment of inertia has to decrease, and vice versa. It has to obey the law of conservation of angular momentum. On the next slide, we'll see an example of this. So in the picture to the right, an ice skater has her arms spread out, that's the picture on the left. Then she brings them in close to her body, that's the picture on the right. As she does this, a couple things happen. And if you've watched ice skating before, you probably already know what happened, but let's talk about why. So the two questions I have at this point are as her arms get closer to her body, what happens to her moment of inertia? And as her arms get closer to her body, what happens to her angular speed? So go ahead and think about that for a second. Alright, so as her arms are getting closer to her body, the question about moment of inertia. It's either going to increase or decrease. So if more of her mass is getting closer to her axis of rotation, like her arms are folding in, so she has less mass further away, that should increase our moment of inertia. Alright, I said increase. It should decrease. Whatever the PowerPoint says. It should decrease the moment of inertia. And this happens because, as our arms get closer, our moment of inertia has to be less, since our arms are less, they're closer to our body, so if our mass isn't as far from the axis of rotation. If you remember, moment of inertia is the sum of the masses times the radius, or the moment arms away, squared. So the closer all the mass is to the axis of rotation, the easier it is to spin, the lower its moment of inertia. As that happens, what happens to angular speed? If you've watched ice skating before, you know that when an ice skater brings her arms in, she starts to spin very fast, or quickly. So her angular speed increases. And this happens because of the law of conservation of angular momentum. As her moment of inertia decreases due to her mass being closer to the axis of rotation, she has to speed up to make sure that that constant stays the same of moment of inertia times angular speed. To recap, make sure you go online and take the angular momentum note quiz on Edmodo, and make sure you bring your notes with you. You should bring these back with you next time we have class, and every class after that, forever. Ever. And thanks for watching.